So I guess we'll do as we usually do. We'll take like 45 minutes to read, and the reading is I've already put it in the link to the Zoom meeting, so I don't have to write it again. You know, we're just going to read the sections from generative adversarial networks through deep convolutional Gans. I think it's like 3 sections on Gans. And so we'll come back at in 45 minutes, which is 10:50 in Pacific time, and discuss.
Cool.
All right. See everybody then. Hi, Terrence. Yeah, we're just going to break to read for 45 minutes. We'll read the first 3, you know, pages 592 to 601, the material that I mentioned in the link to the Zoom meeting.
Okay.
And we'll just be back in 45.
Sounds great.
All right. See you then. Okay, we're back. How did everybody find that reading? Is everybody pretty much able to get through that? Hello? Can people hear? Yeah, you can hear. Okay, great. Okay, so since nobody complained about the time, let's go back to the material. So, so this is sort of the second or the second generational network that we've learned how to build, called generative adversarial networks, and it's built by having a discriminator compete against the generator. The generator is kind of like a decoding network. It starts with encodings, but they're random, and then it builds from them images of the size. In this case, we're building 28 by 28 images from the coding. So there's a short network that does that. Let me find ourselves. Here we are. Yeah, so here's the schematic. Can everybody see what I'm sharing? The book?
Yep.
Yes.
Yep.
Okay.
Yep.
Okay, great. So on the left is the generator. On the right is the real images. And so the generator starts with random noise for the codings. And in this case, I think they're of dimension 100, I think. And then it builds it builds a fake 28 by 28 image. Of course, the first one won't look like this, but after several iterations, it learns to produce reasonable looking images. So the generator's job is to produce realistic looking images that tricks the next part, which is the discriminator. The discriminator is just a simple classifier in terms of its architecture. It takes as an input images that are either fake or real, 28 by 28 images, and then decides whether it classifies them as either 0 or 1, 1 for real and 0 for fake. So the training is done in 2 steps. And so the first part is that, well, let's see. Let's see. Let's see. So the first part, he says you train the discriminator by producing a bunch of fake images and taking some real images together and training the discriminator to recognize them. And he says you just do that for one batch or one. I think he says that you just do it for one batch because it's an iterative thing. You keep going back and forth. Then the next part, you train the generator, and I guess it's good to look at the architecture, the way he builds it. He starts with the generator architecture here, starting with codings, and I guess codings is 30. I was wrong. It's not 30. It's not 100. It's 30. You start with an input of a random vector of length 30, and then you have two dense layers, one that produces an output of 100, one that produces an output of 150. And then you have another layer that produces okay, so these are just linear layers. No, they're actually, no, they're not linear layers. They're linear layers followed by activations. And then the third layer is it takes this 150 and maps it up to the image size, 28 times 28, so it flattens that out. And then it maps that flat vector to, let's see, oh, and the activation, this is a trick that he used before to get pixel values. He's using a sigmoid activation so that, let's see, your, let's see. So it's going to produce an output for each pixel. It's going to produce an output between 0 and 1, and because that's what the sigmoid activation does. And the and that 0 or 1 maps to I think 1 is white, is a white pixel, and 0 is a, no, I think it's the other way around. I don't remember which way it is. I think it's 1 is white and 0 is black. So the probability that the sigmoid output gets sort of translated into the brightness of the pixel, and so that's how you get the image out of this generator. And then the discriminator takes as an input the 28 by 28 image. It flattens it out, runs it through a couple of dense layers with cellular activation functions, and then finally final layer, a classification where it classifies as 0 or 1. And then the GAN model is built as the sequence of generator and discriminator. But it's kind of tricky because the way he initializes it, the discriminator is not trainable. And I think that's, let's see, that's because the first time you run through it, or the second time you run through it, you don't use the, in phase 2, you don't use the discriminator, you just use the generator. So it's let's see, it's a little tricky because it relies on the syntax that that Keras uses. So even though you declare you initialize the discriminator as not trainable, you can change that when you call fit or train on batch method. So he says, well, it's not trainable when we, let's see, it says, so you can use this, I guess, this internal syntax of Keras to make use of the fact that you can declare the thing as, you can initialize the discriminator as non-trainable. And then in phase 1, you're just using the generator. And then in phase 2, you can turn on the trainability of the discriminator. And that's what he does here. So, so here's what happens. Batch size of 32, get the data from the training set, shuffle it, batch it, and then start the training loop. So he has this is the function that he uses to call that, let's see, to call that to call the network, or to do the training, that is. So the input is the GAN model that he built, which is the sequence of a generator and discriminator, the data set, the batch size, the coding size, and the number of epochs. And then let's see, GAN.layers for epoch and range. So he's running through the epochs and running through the batches. And phase 1 is training the discriminator. So he generates some Gaussian noise. That's tf.random.normal. The shape is the batch size, which is 32, and the coding size of 30. And then he produces images out of using the generator with the noise as the input, as we saw. That's how he designed the generator. It takes as an input a random codings vector. That's what noise is. And then it produces as an output the batch of images, of 28 by 28 images. Let's see, then he says, take those generated images together with real images and put them together. And then generate labels for them. And so the generated images, let's see, this is not, okay, the generated images are fake, and so he generates fake labels for them, and the real images are real, so he generates the one label for them. So he's got the new data set of fake and real images, the new set of labels, and then he says, now the discriminator is trainable. So he makes it trainable. So now the second, in phase 2, then he runs, he runs the discriminator, trains the discriminator, that is. Let's see what's going on here. Noise is random noise. So this is also random noise with a shape of the 32 with the coding size of 30. But then this time he puts in labels of all ones. So this is kind of tricky, and I'm still trying to wrap my head around it, but I think I understand what's going on here. So wait a minute. Let's see. So phase one, where's the training for phase one? Yeah, here it is. This is the training for phase one. And then for phase two, he sets the all the labels for the fake images to be one. Then he sets that he turns off the discriminator so that only the generator is being trained on this phase. And then he trains. So this is the training step for phase two. And what I think is going on, he only shows it at a high level, but what I think is going on is that in phase two, the generator sort of scores points whenever the discriminator is fooled into thinking that its images are real. And it's minimizing the loss function. When you minimize the loss function in phase two, it kind of encourages the generator to produce images that fool the discriminator. So you know, by forcing all the labels of the fake images to be one, then if you train that loss function, then every time the discriminator decides that the label is one, that's good, right? So but the back propagation doesn't flow into the discriminator for that step. The discriminator has already been trained in the previous step. So this time, when the discriminator ranks the false image as true, that gets back propagated into reducing the loss function for the generator part of the model. So that kind of encourages the generator to come up with images that will fool the discriminator. Does that make sense?
Yep.
For me, that's the most tricky part of this thing.
That's the crux. Yeah.
Yeah. Why you set the labels equal to 1 on the generator step.
Just to make sure that it realizes that we are kind of fooling it to believe that all the images are true, all are real. In the case of since we are adding Gaussian noises to it, and then we are making sure that they learn from it. Our generator learns from it via the backprop, as you mentioned. So
yeah. So the key part is to realize that in phase one and phase two, you're using you're training different parts of the model, so that in phase one, you're mainly training on the discriminator. You're training the discriminator weights. And in phase two, you're training the generator weights. Or let's see. Or maybe I didn't say that right. Maybe in phase one, you're training both discriminator and generator. And in phase two, you're training only the generator. Does that make more sense? We set the weights randomly. Well, on the first step for the generator, we didn't train it at all. We just set the weights to be random. And then we trained the discriminator. But in some sense, in this first phase, I think we're training both. The back propagation is flowing both into the discriminator and the generator. But in the second phase, we set the discriminator to be non-trainable, so that only the generator weights are being adjusted.
No, but on the first phase, only the discriminator is being trained.
Is that right? Okay.
Yeah, the train on batch here runs at the discriminator.train on batch runs on this X fake and real and Y1. And on the phase two, our whole gan.train on batch runs with the noise and the Y2 labels. So here only the generator gets trained, and in the first phase only the discriminator gets the values. So
But in the first phase, we never turned the discriminator off. We never said generator.trainable equals false. So it seems like
yep.
both are being trained, I think, in phase one. Or maybe I'm wrong. I just don't see how the generator escapes from being trained in this phase.
Not doing it.
But we are
we only
training
call
on
on,
batch. Yeah.
on discriminator. Train on batch, we only call on discriminator, right?
Ah, I see. That's it. Yeah. Yeah, we're just training the discriminator model, but in the second phase, we're training the whole GAN, this thing here. Thank you, Arto. The GAN, remember, is the sequence of the GAN is the sequence of generator followed by discriminator. So in this step, we're training that network, but we're only adjusting the weights on the generator part. And in this part, we're explicitly training only the discriminator, because we didn't even tell it about the generator network in the training part. I'm sorry, this is the part where we set the training. So, we have the generator, but when we call the training, we're only training on the discriminator model explicitly. So yeah, step one is training only the discriminator. Step two is training only the generator. So then he shows that, well, it's not so easy. You do get some results that make sense, but they're not so good. And I guess that some people found out a better way to do this using convolutional networks. And this is the paper they pointed to. Let's see, from Google. Let's see. So they came up with this. The guys who wrote this paper, the deep convolutional GAN paper, came up with this sort of a rubric for training deep convolutional GANs, and why they came up with this stuff, you'd have to read the paper. I'm not even sure they explained it. They just found out that this stuff works. So you replace pooling layers with strided convolutions in the discriminator. That's where you're remember, that's where you're sort of funneling down the network, and then on the other side of the network, the generator, you use the transposed convolutions to upsample things. Let's see. You use the convolutional layers instead of hidden layers. You use ReLU in the generator, except the output layer, which uses tanh. I have no idea why that should be. And you have to use a leaky ReLU activation in the discriminator. I guess these two make sense because a tanh has activations that range between -1 and 1. And a leaky ReLU can make sense of negative. It doesn't just reject negative activations. It's leaky, so negative activations still have an effect on it. So the combination of these two things makes sense, but why? I have no idea why you move to this -1 to 1 instead of the 0 to 1. I don't really understand. Does anybody have insight into that? Okay, so then he says, okay, if you go by this rubric, you can build an architecture that's similar to what we did before, except that it accomplishes, it does things according to the rubric. So he puts batch, so he says, he puts batch normalization in between. He starts with the codings again, but this time he has a dense layer of 7 times 7 times 128. Then he funnels it down to 64 filters so at the end of this, the output looks like 64 by 28 by 28. Sorry, 64 by 14 by 14. Or I guess it's the other way around. 14 by 14 by 64. Yeah.
You're going the opposite direction, right? It's a con 2D transpose.
Yes, he's going the opposite direction, but which is what I said. He starts with 7 by 7, but he goes up to 14 by 14, right? And then another step where he goes up to 28 by 28. Well, at the output of this step, at the output of this step, it's 1. He goes down to 1 filter, but since you're doing con 2D, you're going from 14 by 14 to a 28 by 28. So now you have the end of the generator, which comes out with an image. Then he uses this tanh activation. So the pixel values in this image are -1 to 1 instead of 0 to 1. And he mentions that you have to be careful in your use that same transformation for all the pixels in your images, images that you're going to evaluate on. You have to map them. Normally they would be mapped to 0. The pixels will be mapped to 0 to 1, from 0 to 1, but because you have a tanh layer, the pixels go between -1 and 1, so you have to make sure that all your images are mapped that way. Okay, then in the discriminator, I guess you start with the 28 by 28 image. You do a convolution to get it down to 14 by 14. Let's see, is that, because stride equals 2, so that gets it down to 14 by 14. Leaky ReLU. Something's wrong here. Input shape.
That's in the same layer. It's not the next layer, right? It's just setting the activation.
That's right. That's right. But the input shape is the 28 by 28 by 1, which comes out of the generator. That's right. Okay, and then you do a dropout. He says for some reason he does a dropout instead of a batch normalization here. He says it works better. Then you go up to 128 filters, but a 14 by 14 image. Then finally, let's see. Then this is the activation for that. Oops. Let's see, 20 by 28, 14 by 14, and then finally you let's see, activation. Getting a little confused here, discriminator. So this is one layer. So it starts with the 28 by 28 and ends and puts out a 14 by 14 with 64 filters. Then that's the input to this layer. I'm missing I thought there was going to be another layer here. So here's the other layer. So it's it goes up to 128 filters and 7 by 7. So this layer goes up to so the first layer is 1 by 28 by 28. That is the input. It comes out the output of the first layer in the discriminator is going to be 64 by 14 by 14. Then the second layer in the discriminator goes up to 128 by 7 by 7. And then that gets, so 128 times 7 times by 7 by 7, but then it gets flattened. And so you've got this, 7 times 128, I forget what the number is. That gets mapped to, that's just a classification layer. So it gets mapped to 1 with a sigmoid activation. So there's your discriminator. And then, of course, is just as before, the GAN is the generator followed by the discriminator. There's that number, 6272, which is 7 times 7 times 128.
If I can just interrupt you for a minute, just one very elementary question. I'm referring to this activation keras layers leaky ReLU 0.2 input shape 2828.1. What's the third one for? What's the third dimension for?
Well, in this case, there's the output of the generator is 3-dimensional. It's 1 by 28 by 28, right? So the first dimension is the filters, is the number of filters.
Oh, I see. Okay. Okay.
Yeah.
Thank you.
Yeah. So the first layer here has an output of 64 by 14 by 14 because it collapses the 28 by 28, using stride equals 2. So 64 filters and 14 by 14. And then the next one goes up to 128 filters, but funnels down the activation maps to 7 by 7. And then the last layer flattens all of that and maps it to a single, and then applies a classification. Applies a sigmoid activation to that. Well, it maps that 62, 72 dimensional vector down to a 1-dimensional vector with a sigmoid activation. So yeah, so that's what that network looks like. And then you let's see. He mentions, let's see, this is that thing that this layer uses the tanh activation function. For this reason, before training the GAN, we need to rescale the training set to that same range, right? So that so that when you make your generated images, you're comparing apples to apples with the real images, because the generated images are going to have pixel values between -1 and 1, and the real images are going to have pixel values between 0 and 1. So that's why you have to apply this this transformation on the real images to make them, you double the pixel values and subtract 1, and that maps them to have values between -1 and 1.
Just to make sure, this 28 cross 28 cross 1 is the 28 cross 28 is the dimension of the image, and
Yes.
1 is the grayscale. So only one, how do I say it, the intensity value between 0 and 255, if we represent it in that form. So that's the third dimension here.
Yeah, except I think we're assuming that the input images have already been mapped down to the pixel values have already been mapped to between 0 and 1. I think that happened further up the chain when when we processed the data before we used the autoencoder. We already mapped the pixel values. Yeah. All right. So so he says overall we respected the DC GAN guidelines, except we replaced the batch normalization layers in the discriminator with dropout layers. Otherwise, the training was unstable, and he replaced ReLU with CellU in the generator. Let's see, where's the generator? Yeah, he used CellU in the generator, I remember. So I'm not sure why he doesn't, but he says feel free to tweak the architecture. So this is, I guess this is what I would like to do when I have more time, is just to play with this like he did. See if we can, get.
Does it make sense to replace ReLU with CellU if you use batch normalization? Like CellU is self-normalizing activation function, so it ensures that output is outputs are normalized with like 0 mean and unit variance, and batch normalization is just that. So it looks like CellU is. I wonder if it really affected the training or what.
Well, that's a good point.
Why did
that's a good point. So you're thinking that if you do the if you use CellU, then you don't really need batch normalization here, or?
Yeah, batch normalization we probably need because it it adds some regularization. I don't think you just can drop batch normalization and it not only adds normalizes the outputs, but it also acts like regularization here. So I'm not sure about that. I just curious, does it make really difference to add CellU instead of ReLU when you use batch normalization?
That's a really good point. I think the cool thing is that we have this little laboratory, this little Colab notebook that, he's got a manageable problem on Colab. These things only take, I think it's a few, let's see, a very short time per epoch. So you can actually do experiments and stuff. I think I found out that, well, with the convolutional network, the one we just looked at, I think it only takes 40 seconds per epoch on Colab. Oh, and I know I set it to run, and then I put a comment here, but I forgot to comment it out. Anyway, yeah. So I thought I'd have 25 epochs done by the time we met, but it didn't work that way. Yeah, it only takes 40 seconds per epoch, so you can do experiments and get feedback and try things that So this is a very nice little laboratory that you can play with when you have time to ask and answer the questions like you are, Arto.
Yeah, that's cool. So also, I think it using 10H in the output of generator like makes sense. Like when, for example, doing some regression tasks with restricted outputs. For example, when we do this recommendation systems, for example, in FastAI, they restrict outputs to be if we have scores between say 0 and 5, we restrict it to make model train better. Like it cannot output numbers which are much higher than 5. And basically, we do like a similar thing here. So if you have, for example, value here at the output, it would be much more difficult for this model to learn not to output numbers which are higher than 1, right? So
a ReLU would ignore all the negative outputs, so they wouldn't have any effect on the train. I mean, all the negative pixels wouldn't have effect on the training. So I think.
Yeah, sure, but I mean the positive part. So the positive part, the output is not limited, right? If we have value, and like our realistic images have a range of 0 to 1 if we don't rescale it, like here.
Okay. So in the other generator, in the original model that before we applied convolution, we did something similar, except instead of between -1 and 1, we forced it to be between 0 and 1, right?
Yeah, but I think we didn't did we force it to be between 0 and 1?
Yeah,
or
yeah,
did
the Sigmoid. The Sigmoid.
Sigmoid.
Yeah.
Yeah, so maybe just because 10H is generally easier to train than Sigmoid.
Is it?
I think the reasoning is kind of the other way around, at least the way I understand it. If I agree, ReLU is not capped on the positive side. So he could have replaced ReLU over here with Sigmoid and put everything in the range 0 to 1 and images. That'll totally work.
That's what I wonder. Why didn't he do it that way?
Right. What I think is that the last layer is TANH, which is -1 to +1. But that is getting passed to the next part, right? It's going to the discriminator or the generator. I forgot which one it's going in which order. So you still
generator first, and then discriminator.
Right. So you still want your things to flow, right? If you put a ReLU there, then you're at that stage you're already restricting everything between 0 to anything positive. So then, if there are any negative things that you do want, because this is a gradual phase of training, right? So if you pass more things in that range -1 to +1, it passes on to the next phase. You learn some more, and then you again come back, and then again you're not keeping it between 0 to 1. It's -1 to +1. You pass it to the next stage, and you keep learning. And I think because the TANH works there, hence you are rescaling your input image range. I don't think they first rescaled the input image range and then said, okay, fine, let's put the TANH there. I think the TANH was put in there first, and then the rescaling was done.
Yeah, of course. But I guess the question is, why did they use Sigmoid activation to get 0 and 1 scale in the first in our first GAN, but in this one with convolutional networks, they found it necessary to switch from the 0 to 1 output for the images to a -1 to 1 output for the images. Why? Why didn't the Sigmoid work?
I think it might be better because TANH is linear around 0.
Yes.
And as we have this TANH, stack in like in middle of our model, and the gradients have to flow through back like through the 10H. It's easier to do training when you have 10H than when you have sigmoid, because sigmoid is like it's just harder to train if you have sigmoid like in between between your layers in the middle of the model. Just
So
because,
that sounds good. But what about going back and putting 10H in the original GAN model? Would that work better too?
well,
And
probably,
isn't
I
Sigmoid
guess
just a scaled version of TANH if we are talking in terms of that?
Pardon?
Isn't Sigmoid just a scaled version of TANH?
It's true. It's true. But the point is, why change things that work well? You know, he already found sigmoid worked well. Why switch to 10H? That's the question I have. I mean, I suppose.
I think since TANH works well with ReLU, so that's the reason here. But they have used SELLU, and it works well with that too. So that's the reason. It goes hand in hand with this. Uh, so that's I still have to go into the details of this SELU paper, but yeah, I think that it goes hand in hand, and that's the reason that TinyH is being used here.
You know, well, it'll be interesting if anybody figures it out. Put it on Slack. The only thing that here's an idea that's probably just crazy, but the original GAN takes longer per step. I think it takes well, we saw that the second this version with the convolutional that takes only 40 seconds per epoch, whereas the original GAN takes a lot longer. I think it takes I forget, it's more than a minute. Maybe now that he's saved some time with the convolutional architecture saves time. So maybe now he can use the 10H, because maybe 10H is more compute intensive than sigmoid. Does that make sense? So that Arto was saying is that 10H is attractive because it has a slow, you know, it's symmetric around 0. And maybe we would have liked to use it in the first case, but it would have taken too long, maybe in the original GAN. And maybe this one, because we've saved time with the convolutional architecture, now we can afford to use a 10H. I don't know if that's right.
maybe it's just a good idea which appeared didn't appear before and just appeared now, and so now everybody would use that.
But definitely an art. This is definitely an art because they're not giving any explanations for why they're doing these things. I guess reading the paper is probably the best way to remedy that. I did want to. So this is next time we'll start here with the progressive growing and finish the chapter. But I found this very nice video that I listened to. And he delivers on his promise to explain the math of GANs in 10 minutes. So I thought we could maybe take he has 2 videos actually, and 2 blog articles that go with them. But the first article is he advertises a gentle introduction to GANs, high-level overview, and that's like a 12-minute video. And the next one is this 10-minute video of the math. I thought maybe we could just listen to these 2 videos and then discuss a little bit more on the other side. What do you think?
Yeah, I agree.
All right, let's go then. I'm gonna fix this. You can see the introductory screen here for the first video. Can you see that, what I'm sharing? Okay, yeah. I'm gonna put that up to full page, full screen. And then I'm going to adjust the audio, optimize for a video clip, and then I'm gonna just run it. But I remember I have to turn off my headphones. So hold on, let me do that before I share it. Let's see. I think if I share it with my headphones on, you'll hear it, but I won't. So go off and turn off my. Works. Hello, are you hearing?
Yep.
You can hear. Okay. Did you hear the first part of the video, or should I turn the sound up?
You need to turn the sound up.
Okay, will do. Audio settings. Let's see. Oh, that's not letting me do that. There. And, all right, I'm going to start it again and see if you can hear it. Here goes.
My name is Zach. Welcome to the introductory video on generative adversarial networks, or GANs. This video is meant to give a high-level overview in plain speak, and a follow-up video will dive deeper.
Hearing that okay?
Yes.
Okay, here we go.
Into the math. Let's get started by explaining each of the terms in the title: generative, adversarial, and network. First, let's explain what we mean by a generative model. Quite simply, this means our model can generate new data samples that look like the training data. So, if you're trying to learn images of faces, a generative model could create new, never-before-seen face images. These are examples of generated, totally fake face images, so these are not real people. But the generative model has learned what faces should look like and can therefore create new examples of them. To wrap our heads around this, let's think of a simpler example, like coin flips. We could specify a generative model of coin flips like this. First, draw a random number between 0 and 1. Then, if the number is greater than 0.5, let's say it's heads, otherwise tails. With this, I can simulate coin flips without having to actually flip coins because I have a reasonable model of the process. Here's two data sets. One is from actual coin flips and the other from the generative model as described before. Can you tell the difference? So, this generative model, which consists of pulling a random number and applying a threshold, can give us as many heads and tails examples as we want. Further, the statistical properties of the results, such as the number of observed heads in 1,000 trials, would be about equal to real-world coin flipping data. Now let's talk about the adversarial term. The typical example is that of a detective and a counterfeiter. In this case, we have two adversaries. The first is the counterfeiter, which is the generator, and its job is to create fake $1 bills. Next, we have the detective, called the discriminator, and the job of the discriminator is to tell you if a dollar bill is real or counterfeit. We then set up a game and keep track of who's doing a good and a bad job. If the discriminator can easily distinguish between real and fake $1 bills, then we update our generator to do a better job. If the discriminator is failing and can't tell the difference, then we update the discriminator to do a better job. In the beginning, the generator doesn't know anything about making $1 bills, so it just outputs random noise. However, the discriminator also doesn't know anything about $1 bills, so it makes random decisions. But through time, one will do better than the other, and that will lead to us updating the other one to improve. When the training has converged, the discriminator can no longer tell the difference between real and fake data because the generator is creating samples that look identical to real data. This competition in a zero-sum game between two models is what is meant by adversarial. Let's return to our coin flip example. If you recall, I specified in the beginning that the random number would be evaluated against a threshold of 0.5. That's because I know that a fair coin has equal probability of showing either heads or tails. But what if I have an unknown coin and I want to learn a generative model for that? To apply the adversarial framework, you might do the following. It's worth highlighting that this example is constructed to guide your intuition for how the adversarial framework could result in learning, and it is not representative of how GANs are actually implemented. First, we'll generate our fake data. We don't know anything about the coin yet, so let's pick a random threshold of, say, 0.2. Next, we'll draw 10 random numbers and apply that threshold to get 2 heads. Now, let's get real data by flipping our coin and recording the outcomes. Let's say it actually gives heads 70% of the time, so the threshold is 0.7. So with 10 flips, you might expect 7 heads. Finally, pass these two datasets into the discriminator to get real and fake labels for each dataset. In the beginning, our discriminator has no idea how to tell the difference, so we'll have to pick a random rule. For instance, if the number of heads is greater than or equal to 7 or less than or equal to 3, then we'll say fake. Otherwise, we'll say real. In this case, the fake data has 2 heads, so it's appropriately labeled as fake. The real data has 7 heads, so it's also labeled as fake. So, the discriminator and generator haven't learned anything yet, but we got started by randomly assigning some parameters. In this example, it turned out that the discriminator correctly identified the fake data as fake, but was incorrect in deciding the real data was also fake. Let's now use these results to update our models. First, we'll deal with the fake data. The discriminator was correct, so it doesn't need updating, but that means the generator did a bad job and should be updated. We know that the discriminator gave a fake label because the number of heads was only 2. So the signal we send to the generator is, give more heads. So let's update our generator threshold to go from 0.2 to 0.3. Next, we look at the discriminator's decision on the real data. Since the generator is not involved in this process at all, we can ignore it. If the discriminator were correct, there would be nothing to do, but in this case, it made a mistake, so we need to update it. It made a mistake because it thought 7 heads were too many to be real, but the real data actually had 7 heads. So let's update this upper bound condition on the discriminator to go from greater than equals 7 equals fake to greater than equals 8 is fake. Now, let's run a second trial with our updated models. So our generator creates fake data using the new parameters, and now it has 3 heads out of 10. Let's say our real coin gives us the same data set with 7 heads. Now, let's use the discriminator's new parameters to assign labels to each data set. The fake data gets a fake label because it has less than or equal to 3 heads again. The real data gets a real label because it doesn't violate either of the conditions. In this case, the discriminator was correct in both instances. That means the generator failed in the first case and needs updating. It failed because, once again, it didn't have enough heads. So, once again, we send the signal to generate more heads, so we can update its threshold from 0.3 to 0.4. Since the discriminator was correct in both cases, no updates are required. Okay, one last trial. So with our generator, we create fake data using the new parameters, and we now have 4 heads. Our real data with the actual coin is the same. We have 7 heads. We now use our discriminator to assign labels to each of the 2 data sets. Both the fake and real data get real labels. In other words, the generator was successful in fooling the discriminator this time. Since the generator was successful, it does not need updating. However, the discriminator needs to be updated since it incorrectly thought the fake data was real. It failed because it thought 4 heads were enough to get the label of real. Let's update this lower bound condition on the discriminator to go from less than or equal 3 to less than or equal 4. If you take a moment to think about the dynamics of this process, the generator starts by giving way too few heads, but slowly increases as the discriminator learns to identify it as being fake for that reason. As the discriminator gets fooled, it learns to increase the lower bound on the acceptable number of heads. Additionally, it learns to relax its condition on the upper bound as it makes mistakes on the real data by calling it fake. So, both the generator and discriminator are getting better by competing, and they're learning to do it by using the real observational data as a reference point. Finally, we get to the term network, which, as you might guess, refers to neural networks. That's simply because both the generator and discriminator are implemented with neural networks. The primary reasons are twofold. One, it's well known that a big enough neural network can approximate just about any function, including very complicated ones like the probability distribution of all face images. Second, There's a well-defined and easy-to-implement framework for knowing precisely how to tweak a neural network to make it better if you have examples of mistakes it's made. This is the well-known technique of backpropagation. So there we have it, generative adversarial networks. We can build a generative model of our data, which allows us to create fake samples that look like real samples, by creating this notion of a discriminator whose job is to tell the difference between our real data and our generated data. To implement this in practice, we feed random numbers into our generator network and it outputs new fake samples. We then feed these samples along with real samples into the discriminator and ask it to tell us which is which. By implementing these two models as neural networks, we can use the familiar paradigm of backpropagation to guide us in updating the models efficiently given the errors. So that's the high level of how GANs work. Tune into part 2 for a deeper dive. Thanks for watching.
Okay, let's go straight into the part 2. Video and audio still okay for everybody? Hello?
Yep.
Okay, here goes part 2.
Welcome to part 2 of the series on generative adversarial networks. In part 1, we gave a high-level introduction to GANs. By the end of this video, you'll not only understand this equation, but have learned an algorithm for solving it, as well as seeing how to theoretically prove that if we solve it, we recover the perfect generative model. To get early access to videos and exclusive subscriber content, sign up for my mailing list at blog.zachjost.com. Let's get started by recapping the data flow for a GAN. We start with a vector of randomly generated noise called Z. This noise is the input to the generator, which is a neural network that transforms the noise input into a fake sample. We call the output of the neural network G of Z. Next, we have the real data, denoted here as X. Notice that the output of the generator is the same dimension as the real data. This is indicated here by 3 boxes. Finally, we have the discriminator neural network. The input to the discriminator network is either a fake sample or a real one. The job of the discriminator is to output a single number that represents the probability the input is from the real data distribution. If we use a fake sample as input to the discriminator, the output is denoted as D of G of Z, and this represents the discriminator's estimate of the probability that the fake sample is real. If instead we use real data as input to the discriminator, the output is denoted as D of X, and this represents the discriminator's estimate of the probability that the real sample is real. Since we know which ones are real and fake, we can assign the proper labels, 1 if it's a real sample, 0 if it's fake. Note that this adversarial framework has transformed an unsupervised learning problem, in which we just have raw data and no labels, into a supervised problem with labels that we create. Now, let's take a look at the cost function presented in the paper. This consists of 2 terms. The first represents the discriminator's predictions on the real data, and the second, the discriminator's predictions on the fake data. The first term is the expectation of the log of the discriminator output when the input is from the real data distribution. In other words, if you sample a bunch of real data and give them to the discriminator, what's the average of the discriminator's predictions? Let's ignore the log transformation because that just scales the numbers. The discriminator wants D of X to be a large number because that represents high confidence that a real sample is actually real. The generator is not involved in this process at all. The second term is the expected value of the log of the quantity 1 minus the discriminator's prediction on the fake samples. Once again, D of G of Z is just the discriminator output when feeding in fake samples, and the expectation is just the average of the predictions when you pull a lot of noise input for the generator. Let's take a deeper look at the D of G of Z term. The discriminator wants D of G of Z to be as small as possible, or to have confidence that the fake sample is in fact fake. But since the generator wants to fool the discriminator, it wants this value to be as large as possible, or for the discriminator to think the fake sample is real with high confidence. This sets up the adversarial game. So why is the cost function using 1 minus D of G of Z? That's because this transformation points the desires of the discriminator and generator in consistent directions between the 2 terms in the equation. Remember that the discriminator wants the first term to be large because that's the probability of a real sample being predicted as real. By making the second term 1 minus d of g of z, it transforms the quantity from something the discriminator wants to minimize into something it wants to maximize. So if we add these two quantities together, the discriminator wants to maximize the entire thing, and the generator wants to minimize the entire thing. Hence, we end up with this optimization objective. This merely says to find a g that minimizes the cost function and find a d that maximizes it. Okay, so we have a mathematical statement of our optimization problem. We still need a training algorithm that solves it, so let's step through the algorithm in the paper. For each training step, we start with a discriminator loop. We repeat this loop k times before ever updating the generator, where the value of k is a choice we make. This allows the discriminator to converge before attempting to optimize the generator, although in the experiments of this paper, they just set k equals 1. In any case, for each discriminator loop, we start by pulling m noise samples and using the generator to transform the noise into m fake data samples. Next, we sample m real data samples. At this point, we have m fake samples and m real samples. We can associate a label of 1 for each real sample and a label of 0 for each fake sample. We then pass the samples into the discriminator to get predictions and use our labels and cost function to calculate a loss. We then take the gradient of our cost function with respect to the discriminator's parameters. These gradients tell us how to change each parameter to most efficiently increase the loss function. This is like measuring the steepest direction to walk up a hill. So we update our discriminator parameters to maximize the cost function, or take a step up the hill. This completes the discriminator loop. The generator loop is similar. We start by sampling m noise samples and using those as input to our generator to get m fake samples. Note that in this loop we're only interested in updating the generator's parameters, and this is done by taking the gradient of the loss function with respect to these parameters. Since the dx term only depends on the discriminator in the real data, the derivatives with respect to the generator are all 0. Since we know this in advance, there's no need to waste time pulling real samples and scoring the discriminator on them. That leaves us with a reduced cost function, which we can then calculate the gradient of with respect to the generator parameters and use that gradient to update our generator to walk down the hill. This completes a full training iteration. So that's how you train a GAN. The other contributions of this paper are the nice theoretical results. The authors proved two major points: that the minimum of the cost function is achieved if and only if the probability distribution of the generator matches that of the real data. This means the fake samples are indistinguishable from the real samples. This proof is done in two parts. First, they show that for a static generator, the maximum of the cost function with respect to the discriminator is a constant, and that constant is equal to minus log 4. To show this, let's write out the cost function, but expand the expectation values into their integral form. We can then make a change of variable in our second term so that we integrate over the generator's output directly instead of indirectly through the input noise variable. Now we have an integral over a single variable, denoted here as x, which represents data samples, and each term is weighted by the respective probability of it occurring in either the real data or the fake data. Now, if we were to maximize the expression under this integral at every single point, we would maximize the entire quantity. At any particular point, the form of the equation under the integral is as follows: a constant times log y plus a constant times log 1 minus y, and we want to find the y that maximizes this. To find the maximum for this expression, we can apply the classic calculus trick of setting the derivative equal to 0 and solving to find the extremum. Applying this gives the following equation, which with a little algebra simplifies to this. We continue our simplification until we end up with this solution. If we then plug in the original variables for a and b, we recover our final form for the optimal discriminator. We can easily see that if the probability distribution of the real data and the generated data are identical, then the optimal discriminator returns a value of 1/2. This makes intuitive sense. If the real and fake data are identical, then the discriminator just has to randomly guess which is which, a 50-50 shot. Let's plug this value of 1/2 into our cost function. This just gives a constant of log 1/2 in each of the expectations, which ultimately evaluates to minus log 4, since the expectation values don't do anything to a constant. So we have shown two things: that the optimal discriminator is given by a simple relation of the probability distributions of real and fake samples, and that when these distributions are equal, the maximum of the cost function is minus log 4. Second, they consider the generator, which wants to minimize the cost function. Let's look at the cost function again, and let's plug in our equation for the optimal discriminator to get an upper bound on the loss. Next, let's write down the definition for Kullback-Leibler divergence, or KL divergence, for reasons that will become apparent. Notice that the definition of KL divergence is an expectation value of the log of the ratio of probability distributions. This is precisely what we have when we plug in our expression for the optimal discriminator. Also notice that if we multiply top and bottom of the inner expression by 2, we can pull out the bottom one as a minus log 2 and keep the remaining term on the denominator. This is useful because it enables us to rewrite our cost function as this equation. All right, one last definition. The Jensen-Shannon divergence is defined as follows. This is very similar to KL divergence, except that it's symmetric. This means the Jensen-Shannon divergence from P to Q is the same as from Q to P. This is not true in general of KL divergence. At a high level, think of JS divergence as a distance measure between two probability distributions. Our function turns out to be 2 times the JS divergence between the real and fake data distributions, plus the constant of minus log 4. And yes, this minus log 4 is the very same one that represents the maximum constant cost we incur from having an optimal discriminator when the data distributions match. So this is the final form we've been working toward. Here's the important point of all this math. For an optimal discriminator, the generator is aiming to minimize this quantity. The minimum for any JS divergence is 0, and this occurs if and only if the two probability distributions are equal. So, this shows that this cost function has one minimum, and that minimum is achieved when the generator perfectly maps the real data distribution. When this happens, the JS divergence term would be 0, but this implies the distributions are equal, and then our minus log 4 term falls out, which we separately showed as the cost from the discriminator making coin flip decisions when the real and fake data distributions are equal. So that's the theory under the covers. To recap this video, we showed the architecture of a GAN training process, where random noise vectors are used as input to a generator, and the output of the generator is used as input to a discriminator neural network. To learn our discriminator, we treat it as any other classification problem, where the inputs are real samples and fake samples from the generator, and we try to predict the probability of being real. We then use the positive direction of the gradient of our loss function to update our discriminator in an attempt to maximize the cost, and the negative direction to update our generator to minimize the cost. This process is designed in a way to mimic the theoretical proof that showed that for an optimal discriminator, minimizing the cost function would result in a generator that perfectly models the real data. So our training loops take turns optimizing the discriminator to convergence by locking in the generator and then updating the generator. Ideally, this process is repeated until convergence to the global minimum. I hope this takes some of the mystery out of the math for you. If you'd like another perspective on this topic, I have a 3-part blog series on GANs you might find useful. I'll put a link in the description along with the original paper. And if you'd like early access to videos and exclusive subscriber content, don't forget to sign up for my free mailing list at blog.zachjose.com. Thanks for watching.
All right, so that's those 2 videos. I thought they were pretty good.
Yep.
Any comments or?
Mhm. No, they will be. I just want to ask why did they use JS here? Because JS divergence towards the end. Because I don't think so. Here, it was required in the sense that the Jensen Shannon's property of symmetric distributions were maybe I'm not able to get the clarification behind this, but within the context of the problem with respect to the coin tosses, I don't think so. JS divergence was required. The KL would have done its job.
Yeah, I'm not sure of that either. Maybe we can look in, I think now with that overview, we could probably look at the original paper and maybe get something out of it. So let's see. So this is, it's only 9 pages, which is not terrible. Let's see if he says anything. We'll just do a search for. It looks like, let's see. It looks like it falls out of the, well, he has this expression involving 2 KL divergences, and then he says, well, that's the Jensen Shannon divergence. So apparently it comes out of the derivation. I think that's the answer. It just falls out of the derivation.
Okay. Okay.
But I mean, it would be good to read, you know, to read this paper. So
Okay.
it looks, yeah. Yeah, I haven't read this paper, but now that we've seen that video, I think that one can probably read this paper.
Yeah, I wanted to note that in a video, it seems like training algorithm was a bit different than in Jaron's book. In Jaron's book, we do one training step for discriminator and then move on to training a generator. And in video, he said, like, we train discriminator until convergence, and then train discriminator. So that would be 2 different processes.
Wait, you mean to say train the discriminator till convergence and then train the generator?
Yeah, that's what he said in the video.
Yeah, actually,
and I think I saw it before like that.
If you, Jeremy also, if I recall correctly, in his example, trains the discriminator to some level of convergence, if I recall correctly from his lecture when he talked about Gans. That's my recollection. I could be wrong, but I recall faintly that he didn't just do it for one step.
It makes intuitive sense. Like, you want to have a good discriminator before you train your generator with it, right?
Yeah. So he did, if I recall, Raquel might be able to confirm too, but because it's been a long time since I.
Yeah, he did one of those tricks. Yeah, I think it helps to prevent a mode collapse problem.
Yeah.
So you don't kind of get lost between what is happening there. So you at least have one of them trained decently well. I think, yeah, that's what you're also referring to.
Yeah.
So Raquel, the mode collapse problem you're talking about is when it generates the same images after time and doesn't learn?
Rather, it generates random stuff, and then you basically just spin off in a loop. Your losses don't kind of come down. And that's the weird thing, right? Like, when you're looking at losses in this situation, yeah, I think, yeah, watching that lecture probably by next session will kind of help. A couple of interesting tricks that he does apply there. I think he even mentioned something about, like, how do I put that? Like, when you're training a conventional classification problem, you know you're making progress as your loss is going down, right? And at least you know you're heading towards the right direction. Whereas in the situation of a GAN, you don't know what going down really means. So looking at the loss number really doesn't mean anything when you're training for a GAN. So I think his intuitive or his easiest solution to solve that was print out a batch of images after each iteration. So then you know at least you're moving in the right direction and when to stop and stuff like that.
Yeah, now I do. Yeah, so he's relying on the outputs rather than on loss, which you typically would rely on if you're
Right.
in one direction, so to speak.
Right.
Yeah.
So that's human in the loop, right? I mean, you have to look at them.
Yep. Because otherwise, from what I remember from that lecture also, is like you don't know what the real endpoint or the goal really there is. If you're just looking at the losses, it doesn't really help in that scenario.
Yeah, in fact, that what you just said to what Joseph said to, eventually you would have to have human in the loop, right? In this case, Joseph, otherwise, like, how do you determine the images are good enough?
Yeah.
So you have a human in the loop regardless. The only question is, when do you look, at the end or as you're training?
It just seems like this is where reality intervenes, but the process that was set up and described mathematically shouldn't need a human to intervene. It should, I mean, after all, the network converges towards learning the exact distribution of the images. So you shouldn't need a human to intervene in a perfect world. Right.
It doesn't always, I guess, is because even I recall Jamie saying, he was about to give up on it when it started converging. So it's very finicky, was his comment, even as he did it, that, he was about to give up on giving that lecture when, like, just before he went on, an hour before or something, it converged. And he was like, now I can have something to show, or else I have nothing to show.
Yeah. Well, anyway, this is a really interesting, to me, it's really mathematically interesting. And from the point of view of actually finally, after 700 and 600 pages, we get to a point where we can actually learn the distribution. We're in this chapter, we're learning the distribution of inputs, and that's so that we can then generate fake ones. And that's really interesting to me.
In the current the training loop set up by Gerard, the generator discriminator stuff happens at a batch level, right? Each batch kind of moves. It's not at an level.
That's what I understood, is that you train one batch and then you go, but let's go back.
But by the way, on that, I had a question. Sorry, I was unable to speak for microphone problems. I had a question. The way he does it, just so that, I mean, it's a nit, but I wanted to be sure, because both him and, in fact, the video lecture guys do the same thing. It seems like he's giving 2x the batch size to the discriminator first, and then the batch size to the generator. It doesn't really matter that you're doing that. I mean, it changes nothing, but I just want to make sure that my understanding is correct, because he specifies a full set of batch of zeros and a batch of ones to the discriminator, which is 2x the batch size. And then
so 64 instead of 32. Yeah, I noticed that too. And I was thinking to myself, well, how come it's so smooth and we don't notice any glitches in the training? I mean, isn't there something you have to do to make that happen? But I guess not.
Yeah, that was, so it is 2x and x, right?
Yeah.
Yeah, okay.
Yeah, because you have a batch of real images, 32 real images, and another batch of 32 fake images.
Right.
You just concatenate them together.
Right. Okay.
So back to Rekil. I think Rekil, you had a point or a question?
Just, like I think Arto also is making the same point, right? That the difference in the lecture, in the video that we just saw, was you train one all the way to convergence, the discriminator, and then jump. The way Gerard's doing it is not even at the epoch level, but moving from each batch. So just wanted to kind of point that out and see if that makes sense.
Yeah, and maybe the reason why it works is because we're working with such small images here, the 28 by 28 images, and you don't really have to train more than one batch to get it good. I mean, and then with real images, then that's where you have to train, with really, what I mean real images, I mean bigger images, you would have to do more work to get it to converge.
Yeah, I was thinking the same thing, Joseph. It's 28 by 28 and grayscale. whereas a real image is 3 channels with whatever X, Y.
Yeah. But he did say, as I recall, that he's only going to train the discriminator for one batch to start with in the original ordinary GAN. Right? I mean, just one, he did say one batch. Here's where he says it during training. In the first phase, we trained the discriminator, a batch of real images, sample, blah, blah, blah. Discriminator is trained on this labeled batch for one step. Yeah. Yep. So yeah, maybe it's just because we're dealing with, as Srinivas said, the small and grayscale images, that one batch is enough. And he even says, somebody says, I think the guy in the video said something about that too, where in the example he was showing, it was one batch, but in general, it's, you know, n batches or whatever, a larger number of batches.
Yeah, he said in the paper, they say whatever K is 1, but you do it multiple times, which is what I recall Jeremy did in his lecture, is run the discriminator multiple times before he ran the generator, as Arto pointed out too.
All right, well, we're only 1 minute over, so we actually won't go on. You know, we're basically done on time. So thanks everyone, and we'll see you on Wednesday for the conclusion to this chapter. And if you come in late on Wednesday, just look at the just look at the Slack post, because that tells you what we're going to be reading. You know, I noticed some people came in and didn't know what we were reading, but it's on the post in Slack. You know, I said what we're reading on each night. So yeah, so don't worry. You know, if you come in late, don't worry about it. Just look up on Slack what we're reading. All right, everyone. Thank you so much.